Okay, so our first case study is to write a very short program that uses dynamic linking, and then we try to cheat the dynamic linkers by using our library instead of the system library. The program we call it my test. It's a very short program. Then it just makes a call to the sleep function here. Sleep for 1 second and then quit. Okay. So when we compile this program, we run this program, my test, and we'll see that there is 1 second delay before we come back to the bash shell prompts here. If we run this program normally, it will sleep for 1 second and then it stops. The problem is that this sleep function resides in the libc library, and libc library is the dynamic linking library that will be loaded onto the memory, and when our program runs, it will locate the libc library and then find out where the sleep function is and make the call to the sleep function and then stops and then finish. So we try to cheat the linkers not to link our program with the system sleep function, but to link this call to another sleep function provided by our own. So we write another piece of module, we call this libc, and we don't compile this into running an application, but we only compile it into a library. So in this function, we just print out a sentence, "Oh, I'm not sleeping." When this program tries to sleep, actually it should, we try to make it call our sleep function, and we print out, "I'm not sleeping." Okay, then how we make the dynamic linker to link to our program instead to our library instead of the system library? We have to try to change the value of the preload variables here. Okay, let's see how it works. Now we try to compile libc into an object file. We don't compile with option O here because we don't try to compile it into an application. It doesn't have a function main function here, so we can only compile it to an object file. And we use CCC here to create a library from this object file. So we create a library, we call it libmylib.so. .so is important because it says that this is the library. And behind this is .101, it's just the version. It's not so important. We don't have to type this. So we create a library named libmylib.so, and we add sleep.object here into the library. Now we see that libmylib.so is already in the current folder, in the current directory. Now we cheat the dynamic linker by changing the value of preload variables. We change preload variable points to libmylib.so. Okay, and we export it. LD preload here is just a shell variable, but when we export it, then this shell variable will be inherited by the child process. So it will become the child process environment variables because it's exported, right? So we export it and we run my test. My test will be run as the child process of the current shell. That's why it inherits LD preloads as its environment variables. And when the environment variables point to libmylib.so, then the dynamic linker will link the sleep function with this library, not with the system's libc library. So that's why when we run my test, you will see that it prints out, "I'm not sleeping," instead of sleeping for 1 second. Okay, so when we unset this variable, that means we remove the shell variables away, and we run my test again. And my test will sleep for 1 second because the dynamic linker now don't see any preloaded library specified anymore. So it looks it looks for the libc standard library and find the sleep function there, and that's why when we run my test again, then it sleeps for 1 second. So you see that whenever we change this preload variable, then we can cheat the dynamic linker. When we run my test, it looks for another function with the same name, sleep, and it is our target of attacking this program. So you see, if this my test is somehow a set UID program, then we can run this piece of code with the UID set UID version priority. But there is a countermeasure. That means people creating Linux, they have already patched or fixed this security problem. So let's take a look at if we change my test into a set UID program. First, we change this to the root owned by root user, and we turn on the set UID bits. You see, my test is now a set UID program because it has a set UID bit turned on and is owned by root user. And we export the preload to point to our own library, our cheating library here. We run my test, it doesn't work. It's still running the system sleep function. It's not at our expectation. We cannot take over the system, simply because the dynamic linker today has already patched or fixed the error, the security problem. So when a dynamic linker when our program runs and the dynamic linker try to find out the missing piece of code, it looks for the dynamic library specified in LD preload and LD library. But the problem is that if it is a set UID program, that means the effective user ID and the real user ID are different. If these two are different, then the dynamic linker will not use these two parameters, two variables. If the dynamic linker don't look for the libraries specified by these dynamic linkers variables, then it still use the system sleep function. That's why we don't see our piece of malicious code running here. So the mechanism, the countermeasure mechanism is that whenever we run a set UID program, then the dynamic linker will ignore these two variables. If it ignores these variables, then it doesn't look for our malicious libc function here. So that's why today we cannot use this kind of attack to get root privilege anymore. Now, to understand how the dynamic linker ignores these two variables, we run a simple test here. So first we use env program. Okay, we copy the env program into another program owned by our own. So we make a copy into my env. My env now owned by Cedar. We make this program to be a root set UID program. We change it to root user, owned by root user, and turn on the set UID bits. You see now my env has the set UID bit turned on. And if we try to change these two variables by changing preload to point to our malicious library and export it, we also change the dynamic library path to our current directory and export it. We also export another variable start with LD, but it is just for testing. So we set LD my own is the string my own value. This is only for testing. If we use the original env program, when we run this program to bring out all the environment variables of the child process, and we grab to sort out, filter out only string that start with LD, then we see all these three variables are inherited by the child process. So we see preload, library, my own are all variables of the child process. Because env is not a setuid program, so the dynamic linker will allow all these three variables inherit to the child process. But now if we run our setuid program, setuid program is dangerous because if we have a mistake inside it, we can allow attacker to take over the system, runs with root privilege. Now we run my env, and now we only see that LD my own variables is inherited to the child process by the child process. These first two variables are ignored by the dynamic linker. So dynamic linker will try to remove this out. Okay, the system will try to remove these two variables not inherited by the child process, because this is dangerous. When we run a set environment variables, then LD preload and LD libraries are ignored. That's why we cannot exploit this security problem any longer, because it's already fixed. So let's take the case of Mac OS operating system Yosemite version again. Last time we talked about this dynamic linker. It uses an environment variable named print to file here. Allow user to specify a file name so that all the log message of an application will be printed to this file. The problem is that this dynamic link library is a setuid program, and when it prints out to this file, it doesn't close the file. So when it doesn't close the file is still open. And if we know the file descriptor, we can write to that file. So this is the attack. We try to set this variable to a file that we don't have the right permission, etc sudoer. Sudoer is a list of all users and their permission when we run the su command. Su command is to switch user, su, okay? Then we switch user to Bob, okay? So that we will export this variable, okay, to the actually there should be export here. We export this variable to the process running by Bob, which is a shell. Okay, so in the shell, we have the right permission to this file because the dynamic linker doesn't close the file, so the file descriptor is free and it's still open. Then we write this string to this file. Because the file is still open with file descriptor number 3, so we inherit the right permission. So we write this string to the file as sudoer, and we add Bob to the list with all the power and no password at all. So Bob now becomes root. So that's how the attacker attacks Mac OS, using just an environment variable to write to a file that they don't have permission. Okay, so we need to clarify a bit on the differences between exec and system. System function call allows us to execute not only a binary program but also a shell script. That means any command we type on the shell can be run by the system. A system you fork to create a child process, and in the child process it executes execl to run bin shell, and when bin shell runs, this shell will run the command specified by system. For example, when we have like a function like system and we run ls here, ls is a command in the shell that prints out the file in the folder, right? So what this function call does is that it creates a child process here. This is a child process, and this child process running bin shell, okay, running a shell, and the shell runs the command ls, and that's how ls is run by the system call, by this system call. So actually the child process will inherit all the environments provided by the parent process, and this is the way attacker can try to manipulate our system. But system is very good. It's very commonly used because it allows us to run a shell, to run a command. So we don't have to provide this command as a binary program, but it can be a shell script. So it's very convenient. And after finishing the child, we go back to the parent process and running the remaining instruction. Another set of another family of exec is that execl, exec env, etc. But they are similar. When we run exec, then we don't create. When we run exec, when we run exec, when we run exec, for example, ls, then the current program here with exec here will be overwritten by the ls command. The ls is copied into the current process and override the current process. Okay, so it doesn't create a child process. It takes over the memory of the current process and runs it. So that's why when this process runs, it doesn't inherit all the environment variable of the parent process, of the original process. Only selected environment variables are passed to the new process. And when this process finishes, it doesn't return to the original program because the original program is already written over. Okay, overwritten by the new process. So its code is gone and the new code is overwritten here. So that's the difference. Exec is more safe, it's safer because it doesn't inherit all the environment from the parent process. But it's less convenient because the system here run a shell, so we can provide a non-binary command here. That means we write a shell script and we can run it here, while exec can only run binary system, binary command. Now we try to make another the case study where we change the path. We don't attack the dynamic linker anymore. Remember that we have different attack surface at the beginning here. It is here. We finished with the dynamic linker. Now we try to attack another parts of application. The first case study we also already try to replace another library with the system library with another library. Now we try to see the second case here. When an application runs an external program, we try to cheat the system command by running our own program instead of the program expected by this application. So we do it like this. We try to change the path environment here. Okay. This is a program. This program is very simple. It uses system call to run a program named Cal here, which will display the calendar of the calendar on the screen. So when this system call runs, it displays the calendar like this. Okay, and Cal is the binary command in a shell. So when we make system call, it displays the calendar. But it doesn't specify, this one doesn't specify the path to the Cal program. So the system, when it runs the Cal command, it doesn't know where Cal is. So it had to rely on the path variable. So the path variables has a specified like this. I can echo the path variable here. You see that it points to, for example, user local sbin here. So it knows that where the here actually this is where this is where the Cal command can be found. So by looking through all these paths, it finds where the Cal command is. Okay, the Cal program locates here. So the path helps the system call to find out where the binary can be found. So we cheat this by changing the path so that it points to our program first. So instead of calling this calendar program, we write another calendar program with another program with the same name, Cal, but it doesn't display the calendar. It runs another system call, but to run bin bash, we have to run bin bash with option P here to turn off the countermeasure. Okay, otherwise bin bash has fixed the problem, has fixed the security problem. So we have to turn it off by this option P. So our malicious program runs a bin shell instead of displaying the calendar of the system. So we do it as follows. Our first program, we call it vulnerable program, a program that can be attacked. I'll compile our vulnerable program into val, make it a setuid program, and when we run it for the first time, it displays the calendar. It's good. Now we compile our malicious program with the same name, Cal, here, and we change the path. The original path is here, and we add a string dot here in front of it. That means whatever the program, whatever path the program looks for, it has to look for first in our current folder. So it looks for the Cal. When it runs Cal, it looks first in our current folder, and this is where the program, our Cal program, resides. So okay, we echo path. Now we see that current folder has the highest priority for looking for a binary program. So when we run vulnerable program here, it looks for the Cal program by searching these paths. So it looks for the Cal program first in our current folder, which is our malicious program, and it runs a shell. That's why we have a shell here, and this is a shell that runs with root permission because this is the setuid program. The vulnerable is the setuid program. So we run ID, we see that we have the effective user is root. So we take over the system simply by changing the path here. Point first to our current folder, and instead of the system count program, we replaced it with another program named count with the same name. And when the vulnerable program here runs a system call, it runs our system, our program, instead of the system calendar program. So in this case, we got the root shell, we take over the system. Great, right? So using system is more dangerous because system will inherit the path environment. If we use execv, it's safer because we can select which environment variable will be passed to the new program when we run, right? Because system creates a child process, and the child process inherits everything, every environment variable from the parent process. So the attacker can change the parent, a variable from the parent process, and then becomes environment variable of the child process. But execv, we can specify which environment variable will be passed to the new process. That's why it is safer. So it's still recommended that you use execv instead of system. But people still use system simply because system is more flexible. It allows us to run not only binary program but also shell script. And after running a child program, we can come back and run another program, another instruction behind it in the parent program. But with execv, it overrides the parent program. When we execute a command, we cannot come back to the parent program anymore. Now we come to attack to library. The library, which is another here, library is this surface of attacking. Yeah, now we talk about library attack surface. Okay, when we attack this kind of libraries, then we can change the path to the library, so that when we link a program, we may choose another library instead. This situation, in this case study, we use a local library of Linux and Unix. Local allows us to use the different language for as an interface for different program. Our program can be an international program. That means it provide user to select different language when they run the program. For example, we use get text, we can translate a message to another language. This program brings out how to use this program, the uses of this program in English. But if we use get text, we can translate this message in English into another language. For example, Vietnamese. Of course, we have to have some library for this. Okay, but I haven't prepared any library for you, so you don't see the translation when you run this program. How do we specify the language that will be translated? We use these environment variables. Lang, for example, we specify lang to be when we specify lang to be, for example, we specify an environment variable. Lang is the vi in capital, like this. Okay, if we specify this and we run our previous program, then the message will be translated into Vietnamese. Okay, that's good, because we have a program that we can change the parameters, variables, environment variables here, and have the display in different languages specified by user. So that means user can specify the language, and when user run the program, they have the display message in their own language. That is good, right? But the problem is that attackers can create a translation, a very different translation of the message. And if we run printf, we don't have the translated message. We have a string provided by malicious user or provided by attackers. Attacker can make this string, for example, use the file name, translate it to another string, but it is not the correct translation of this message, but a string that contains something manipulated by the attackers. And if attacker can put the input to the printf function, then they can take over the system. How to exploit the printf function will be addressed in another lesson later. I think in the 6th week. Okay, week number 6 will address how to attack a system via the printf function. So if attacker can modify this string, they can attack our system, our application. So the other attack surface is the application code. This is the last one. If we have a program, and this program use an environment variable, then there is a security hole. For example, this program use the get environment function to get the value of an environment variable, PWD, present working directory. Okay, the present working directory is a shell variable that keeps the current working directory. So we can get to know that which directory we are in when we run this program, and we got a string return and pointed by this pointer, and we print the return pointer here into a string, another string. We print out this string as the present working directory is, and then the present working directory. We bring everything into this string, and lastly we print out the target string out to the screen. So this string should look like present working directory is, and then we print out the working directory. So this program is very simple. It looks harmless, but actually there is a buffer overflow issue. This string is only 60 bytes long, and if we provide this string for this string becomes too long, then it can override the memory of allocated for array here, the array variables here. So the problem is that we can make this string as long as we want by making the present working directory really long. So how to do it? We look at this. Okay, the command in lower capital here, present working directory, print out the present working directory for sure. But there's also another variable in capital, $present working directory. This is a shell variable. It has the same value here. Whenever we change the working directory, then this variable is also updated. So that's why we cd out one level. Now we see the content of present working directory is home seed. We go out, then the content is only / the root directory. Okay, now if we change the shell variable to xyz here, and the current directory when we run this command is still the root directory, but when we echo the content of the shell variable, it's xyz. So these two are now different. That means we can change the shell variable to any string we want. So we can make this string really long by specifying it like over 60 bytes. And if it is over 60 bytes, then we create a buffer overflow here. and we can crash this program. Or better yet, whenever we have a buffer overflow problem, we can override this program with some code specified by attackers, and we can take over the system. This will be the topic of, I think, in the next 2 weeks we will talk about buffer overflow security problem. So there's a secure way to do it. Instead of using get environment, we can use another safer version of Unix or Linux, is secure get environment. When we use secure get environments, then we have the value of the environment we want to get if it is not a setuid program. So when we run get environment, the original get environment, you see, it searches for the environment and return a string value, the string value of the environment variable. So we can get any environment variable returned by get environment variables. But if we give set secure environment, secure get environment, this function will check if the effective user ID and the real user ID are different. That means this is the setuid program. Then the secure execution will ignore some environment variables that are considered dangerous. For example, the path environment variable will be ignored. The LD preload environment variable will be ignored. So if we don't have the return value, then we cannot get infected by the attack. So instead of using get environment, then use secure environment. If the variables is considered dangerous, then the return value we have is only null. Okay, so null is safe. But get environment return any environment variables. It doesn't differentiate whether we run a setuid program or not. So this is for the conclusion of today's lesson. We remember that in order to make the Superman delegate his superpower to somebody else, we have two different approaches. The first approach is that we create a setuid program. If we are a normal user and we want to change our password, right, then we have to run the program with the setuid bit turned on. So when a normal user run a setuid program, they have effective user ID or effective permission as root user, and they can do with special root permission. If you want to change your password and you run the password program, it's a setuid program, then you can change your password. Even normally you don't have right permission to the password file. The challenge, the difficulty we have here is that we have the environment variable in the between. User can change the environment variables, and when the setuid program runs, it also takes the environment variables, which can be set by user. So that is where the security problem arises. Attacker can modify the environment variables, actually shell variables of the of the parent process, which become the environment variables of the child process. So normal user change the environment variable. So when the setuid process runs, it takes the environment variables here. Some of these values have already been changed, which become the bad input for the privileged program to run. So that is dangerous. Another approach, which is commonly used by Windows and Android, is that normal user don't run a setuid program. A setuid program, here we call it a privileged process, is running as a server in the background in the operating system. It occupies memory all the time, and it also requests for the CPU to run. So it runs in the background. Whenever user wants to change his or her password, for example, then the privileged program here will run and provide service to user. User provide the current password and log name, and the privileged program here will change the password file and return the state to the successful state to the normal user. So normal user, they don't run a setuid program, but as a running privileged program to do the specific task for him. This specific task also takes environment variable as its input, but user cannot manipulate the value of these environment variables. This environment variable can only be set by the root user. Okay, the root user, when they run this privileged process, and the privileged process inherits some environment variables, but these environment variables can only be modified by the root user. So normal user cannot change these environment variables. That's why this approach is considered safer. Unfortunately, Linux and Unix are using setuid approach, but Windows use the service approach here. This one safer, and Android, even Android operating system, Android is developed based on Linux, but when they built Android, Google removes all the setuid and setuid mechanism out of that Linux kernel. So Android also use this service approach, so it's considered safer. But this approach requires the process to run all the time, so which takes CPU and occupies memory, while this approach doesn't require the privileged process to be run all the time. So we have we have more memory here, but there is a trade-off. Okay, less memory but more security problem here. More memory occupied, but less security problem. So that's the whole things we learned today. Okay, so before I terminate the lesson, I will show you the folder of today's lab work that you need to complete. Okay, we take out the security folder that I have shared to you. Lab version 1 and lecture 2, environment variables. So you see that all the code needed for the experiments of this lesson are already here. I already provided everything here. So you try to repeat whatever we have learned at home. Okay, and here is the assignment. What you have to do. Oh, it's loading really slowly because I'm still recording and my machine is out. Okay, so here it is. I have listed out all the tasks that you have to do. Most of them are just repeating what we have presented, or what are on the slide. Okay, so you look at slide 3 and you repeat the task here. Okay, and if there is some code that you have to write, you can already you can find it here. Okay, these are all the programs needed for the experiments of this lesson. So please complete this task. We don't have time to do it within our lesson time, so please do it at home. Okay, it's pretty simple and easy. Just repeat the task of the corresponding slide here. Okay, if you cannot do it, And next time, before beginning the next lecture, you can raise up your question and ask me for help. Okay, so that is all for today's lesson. Do you have any question? So any question? Okay, so if you don't have any question, then okay, good. Then we stop here. Remember to do the homework, okay? Okay, so bye for now. See you next week.